Welcome everyone, this is Professor Nick Lohr from the Virginia Tech Math Department, and we're starting our course on modern algebra, Math 3124, with, let's start with sort of an introduction to give an overview of the ideas that we'll be looking at throughout the semester. You've all taken algebra in some form, of course, in high school or elsewhere, and you might be wondering, well, what on earth are we doing with this so-called modern algebra? What is that? And so I'll try to give you a broad overview of what that is here, and then we'll have many more technical details, of course, as we go through the class. So our goal in this class, in modern algebra, is to learn about abstract algebraic structures such as groups, rings, and fields. Groups, rings, and fields. Now, these words are technical mathematical words that have long definitions that we'll come to in time that mean very different things from what you think they mean from you're using these words in English. And rather than just give you all those definitions now, which would take a long time, today I just want to give you some intuition for what are these structures, why would you care about them, and what could you do with them. So let me just say a few words about each of these, starting with groups. So a group somehow is a mathematical construction that lets you measure the symmetry in a system in a rigorous sort of quantitative way. So it's some sort of an object, I won't define it yet. But one of the purposes of the groups is to look at symmetry. And so what do I mean by symmetry? So imagine geometric shapes, for example. We could draw various triangles. Here's a triangle. Here's another triangle. Various triangles. And somehow this is supposed to be an equilateral triangle, all three sides equal. This is an isosceles triangle where two sides are equal, but the third is unequal. And here's a scalene triangle. And intuitively, or aesthetically, you might say, well, this equilateral triangle has a lot more symmetry to it than the others. This is more symmetric than the scalene triangle. And then you could even draw other shapes as well, like maybe a snowflake, or some sort of abstract depiction of a snowflake. That seems to have maybe even more symmetry than the equilateral triangle, maybe. Or if you want, you could have like a circle. And somehow the circle seems to have way more symmetry than all the other shapes that I've drawn. You could have a square. You could have a rectangle. Various things, all sorts of shapes. And for each shape, there's actually a group. Well, I haven't said what a group is, but there's a group that tells you exactly how much symmetry there is. And this group is sort of more complicated than this one because there's more symmetries in the figure. And I haven't even defined what I mean by symmetry. Right now it's just this artistic notion. But we're going to give a mathematical construction that captures that idea. And that's going to be very powerful. So that's some intuition for groups. Let's do fields next. What's a field? Well, a field, intuitively anyway, is some kind of a number system where all of the arithmetic operations that you're used to, like addition, subtraction, multiplication, and division, are all possible. So think of a field as like a generalized number system. Where all those operations are possible. addition, subtraction, multiplication, division. Well, division, of course, by non-zero. You can never divide by 0. And whether you realize it or not, you're not using the name, you've all worked in fields before. There's some familiar examples of fields, just to make sure you understand what I mean. Like the real numbers is maybe the most famous one. I'll introduce some notation here. The special R for the real numbers, you can add and subtract, multiply, divide by any real number by another. But then that's not the only one. So for instance, you could look at the rational numbers, Q, a subset of the real numbers. Basically the fractions A over B, where A is an integer, B is an integer, and B is not 0. Not all real numbers have that form. But if you work with fractions, you can add, subtract, multiply, divide. You always end up back in Q. And so you can do everything. So Q ends up being a field. And I'm sure some of you have seen in linear algebra or somewhere the complex numbers, which are needed for various purposes, where you have a square root of -1. That's sort of a bigger field than R. You can still do all the stuff. You can divide complex numbers, multiply them, and so on. So that's a field. But then there's way more fields, and just to mention one that's a little bit more exotic, you could actually just take the 2-element set, 0, 1, that's called the integers mod 2. Some of you may have seen this elsewhere, and you can just basically come up with very silly rules for adding and multiplying, like 1 plus 1 is 0, and 1 times 1 is 1, and so forth. And that, even though it's a really small set, you end up being able to do everything. All the 4 operations, so that's a field. Okay, so and there's all these other fields that you haven't even imagined that we'll see later in the course. Okay, so fields. Now, what about rings? What's a ring? Intuitively, and this is all intuitive. I'm not giving you the definitions yet. A ring is kind of like a field. You can still think of it as some kind of a number system, but now. The key difference is that you have to be able to add, subtract, multiply, but you don't always divide. That's not always possible. And there's all sorts of rules, like the distributive law and so on, that you have to have to be a ring or a field. I'll get to those. But the main thing now is, like, what are the operations that you expect to be able to do? So plus, addition, subtraction, multiplication are possible and obey various laws, but maybe division doesn't always work. I'll say division is not available. And another way to say that is that not everything in this number system, maybe not everything has a multiplicative inverse. Like 1 over x. And that might seem strange. It's like, when's that going to happen? But in fact, you've also seen a bunch of rings already, where this exact phenomenon happens, and yet the ring is still useful and you want to work in it. I'll just give you 3 quick examples of rings. The most maybe famous ring is the integers. Z, the set of all integers, including negative integers. You can add, multiply, subtract integers. But you can't divide all the time. For instance, 2 and 5 are integers, but 2 divided by 5, that's not an integer anymore. So 5 doesn't have an inverse that's still an integer. Okay. Of course, you go to Q, but if you want to stay in your set Z, you don't have division. Okay. Another thing you could consider that you've probably seen somewhere in an algebra course in high school or whatever, polynomials. And say one variable x. Maybe things like 3x cubed minus 5x plus 7. That's a particular polynomial. You can add and subtract and multiply polynomials, then you always get polynomials back. They satisfy all these nice properties like the distributive law. But you can't really, like if you look at 1 over x, for instance. X is a polynomial, but 1 over x, that's not a polynomial anymore. And so if you want to just only work with polynomials, you're in this ring here that's not really a field. And one more example that you've definitely seen if you've looked at taken linear algebra, if you take, say, square matrices over the reals, maybe, in real entries, for a fixed size, like 3 by 3 matrices, let's say, you're probably aware that lots of matrices, not just the zero matrix, lots of matrices do not have matrix inverses. You can't invert them, and therefore there's no division. You can multiply matrices and add them and subtract them. So this is a nice ring where another sort of weird property, though, is that the multiplication of matrices isn't commutative. You can take 2 3 by 3 matrices saying A, B, and it's very often true that A times B is not equal to B times A. And that's something, at least in rings, we will allow that. It's called a non-commutative ring. Although in fields, I didn't say it, but in fields the multiplication does have to be commutative. But these structures come up like matrices where you don't always have inverses. So this is one of the reasons that you want to have rings available, not just fields. Okay, so that's a first little glimpse at what these kinds of these structures are. And I'll continue in just a moment with some history about where all this stuff came from. All right, so the history. So, you know, when you first take algebra, you don't do all of these weird number systems, and certainly the people that first discovered algebra weren't doing it either. So where did it all come from? So let's start with a very old problem that's been looked at for a very long time that you've definitely seen in your original high school algebra course, the idea of like solving a polynomial equation. Among many other kinds of equations you could look at, basically linear equations and so on, but polynomial equations are more interesting. And if you sort of went down the street and asked people about whether you learned in algebra, one of the first things they would probably say is the quadratic formula, as an example. The quadratic formula, and this tells you if you're trying to solve a degree 2 polynomial. So let's say you have the coefficients, maybe a, b, and c, where a is not 0. You want to figure out an x, let's say a real, or even could be complex, I'll just say real, that solves this degree 2 equation. Ax squared plus bx plus c is equal to 0. And as you all know, the solutions, possibly complex, I guess, assuming a, b, and c are real, are given by this nice formula. Negative b plus or minus the square root of b squared minus 4ac over 2a. All right, and again, this is what you would probably think of as algebra before taking this class. You know, here's an equation, let's solve it, using these operations that we've talked about and also the square root operation. All right, so that's great, and this has been known for a very long time, by the way. The Babylonians in 2000 BC knew, at least in the case of examples, knew some version of this formula, as did other civilizations. Now, something that wasn't known for thousands of years after that is, well, what if I had a degree 3 polynomial? Okay, what if it was a cubic and I wanted the roots? Or degree 4, degree 5? Okay, well, it turns out that those are a lot harder than degree 2. It gets much harder as the degree goes up. But it can be done if you have a cubic or a quartic. And this is called the cubic formula. And so this solves a degree 3 polynomial and gives you the answers. I won't write the formula down. It's quite complicated, but there is a formula. Okay? And there's a quartic formula for degree 4. Probably haven't seen these in high school. They're exceptionally intricate formulas. These were discovered, I think, around the 1500s. And various people, in particular René Descartes, who you might have heard of, he was one of the people that figured out how to do the quartic formula. And so this was great progress, although it took a long time to get there. But the natural question then was, well, okay, what about degree 5? What if my initial polynomial is a 5th degree, ax to the 5th plus dot, dot, dot? How am I going to solve that? So people looked for the so-called quintic formula. To solve degree 5 polynomial equations. I won't write all the terms, but the top term is some a times x to the 5th. And they looked for a long time, and they did not succeed in finding a quintic formula. And the reason is there is not a formula. There's no such formula. Not just that we haven't found one, you can prove there is no formula of the form. I haven't really defined what I mean by a formula, but that can be done, and you can define what you mean by a formula, but then you can then prove there's no such formula. And this was a major advancement in mathematics and in the knowledge of humankind due to various individuals, Abel, Ruffini, and most notably someone named Galois, proved that there is no quintic formula that will always solve every generic degree 5 equation, no matter what the coefficients are. And this is an astoundingly, it's one thing to find a formula and like sort of check that it works, but to show that there couldn't possibly be any formula of any kind is way beyond that in terms of how difficult that is. And in fact, all these ideas from group strings and fields that I've alluded to were developed in the context of this problem, showing that this polynomial equation couldn't be solved. And that's not something we'll get to in this class, but I'll just give you a hint as to the idea of what you do, again, to try to motivate why you'd want to learn about group strings and fields. So the proof idea is that you take some polynomial of whatever degree, and you use rings and fields and things to build a group that somehow measures the symmetry of the polynomial and the roots of the polynomial. So all these structures are coming in. So symmetry of shapes, I discussed earlier with these triangles, for instance. You can sort of see, at least in some intuitive level, that there's different levels of symmetry in these triangles. It turns out the same is true for polynomials and their roots, but it's much less obvious how that's going to work. And I'll just mention, in case you're curious, that, for instance, this cubic polynomial, x cubed minus 3x squared plus 2x, in some sense has the same amount of symmetry, namely not very much, as a scalene triangle, whereas x cubed minus 1 has, in some sense, the same symmetry as an isosceles triangle, and this other one, x cubed plus x minus 1, although it might not look like it, the roots of this are very symmetric, in the same way that the equilateral triangle has lots and lots of symmetry. So I won't try to explain how that association happens. That's very intricate. But just to give you an idea, And then the weird thing is, if the roots of your polynomial have too much symmetry, and when you get to 5, there can be lots and lots and lots of symmetries, so you have a complicated group of symmetries, it turns out you just can't get that formula that solves it. And that first kicks in when you get to degree 5. And this is basically the famous result in a subject called Galois theory that's much more advanced than this class, but it ties together all the things we'll be learning. And I should mention maybe the dates here. So Galois lived from 1811, if I wrote it down correctly, to 1832. So you can calculate his age. He died in a duel, by the way. But before that, 21 years old or whatever, 2021, he did all this stuff. It's like unbelievable. Like we're all in college learning these basic things, and Galois had already proved this incredible result right before he died at the age of 21. Okay, so this is one of the things that led to the development of all this abstract stuff. Okay, and let's see. Ooh, so I'll continue in just a second. So with that history out of the way, let's just move on to mention some of the many applications of this subject, abstract algebra, modern algebra, in various other fields. So, for example, physics. Well, when you think about molecules and stuff, there's a lot of symmetry in the shapes of molecules and things. And indeed, when you look at, say, crystals, crystallography, you get to have a bunch of symmetry groups there. Quantum mechanics uses quite a bit of abstract algebra. A very modern, well after the 1800s, a modern application of algebra came up in cryptography. So when you're sending secret messages or you want to keep your message secure, there's these things called public key encryption that makes great use of groups and fields and rings. Digital signatures to prove that you authored a document that you're sending. And things like error correcting codes. When you have say you have a CD that gets scratched and the data is partially corrupted, but you can still listen to the CD because of this algebraic construction that they use to encode the data with some redundancy in there. That uses fields and linear algebra and stuff to actually do that. Art, of all places. Maybe this isn't so surprising when I start talking about measuring symmetry, but you can use algebra to kind of classify just how many types of symmetries you can have in something like a wallpaper design or a frieze, which is kind of like a one-dimensional version of wallpaper. And there's also the crystal groups, which is like the three-dimensional version of that. And algebra, like so many subjects, also has applications within mathematics itself. So you can apply algebra to solve problems in other areas of mathematics. If you think of that as an application. Most notably, number theory benefited greatly from these algebraic ideas. And maybe surprisingly, geometry did as well. And I feel I should say just a word or so about that. I mean, it might seem surprising. Why is algebra related to geometry? They seem like very different subjects. But in fact, speaking of things that are impossible, so we talked about these, you can't solve this quantic equation with a formula. There's various things you're trying to do in geometry. construction problems. Which you may have heard of, where you just have a ruler and a compass, and those are the only tools you're allowed to use. You can draw straight lines with a ruler, you can draw circles with a compass, but that's it. And some of the problems that people looked at for a long time were like trisecting an angle, trisecting an arbitrary angle into 3 equal subangles. Or maybe there's something called doubling a cube, where you have maybe a unit cube where the side is 1, the volume is 1, and you want to make a segment basically of length cube root of 2, where the volume would get doubled. But you want to construct that segment that have exactly the right length so that would be the volume. The most famous one of all is sort of called squaring the circle. Where maybe you start with a circle, which of course you can draw with a compass, of radius 1, and you want to somehow make another line segment that builds a square with the same area. And you can figure out quickly that would have to have side length square root of pi. So how do you make a segment of that length, starting from a segment of length 1, just with a ruler and compass? And then things like you know, and you could inscribe a hexagon in a circle. Maybe you want a 7-sided polygon, a regular 7-gon. In a circle. All right, and it turns out that all of these things that I've just written down, these construction problems, are impossible. They cannot be solved with ruler and compass. There's plenty of other ones you can do, like bisecting an angle or squaring different kinds of shapes that aren't circles, like triangles and stuff, or making hexagons or octagons, and so on. But these are possible. No matter how clever you are with your construction, there's no way to do it. How do you prove that? Okay, the proof of impossibility is much harder than a proof of existence, where you just give the construction and prove that it works. Okay, they're impossible, and I certainly won't give you the proof here. It's very long, but I'll just mention, shockingly, that these things I've been talking about, like fields, number systems where you can add, subtract, multiply, and divide, has nothing to do with this. That's the critical ingredient that you need, along with some linear algebra as well. Field theory and linear algebra, which you can think of as part of ring theory maybe, provide the key tools, the technical tools that are needed to complete these impossibility proofs. All right, and as a side comment, another big goal for us in this course, I should mention, we're not going to talk about any of this stuff in this course, or just barely allude to them after today. You can take later courses like 4175 and so on, various physics courses, various art courses. There's a geometry course at the 4000 level that does all this stuff. Our goal here is much more modest. We're just going to provide the foundation that you need in groups, rings, and fields, and to help you move on to all of these more exciting topics. Okay. So again, just to state that one last time, our goal is to provide that foundation. What are the definitions? What are the basic properties of groups, rings, and fields? And as a second goal that comes very closely related to that is we want to build our skill at writing proofs, which you've already taken a proofs course, but it's considered that you're not just automatically used to that after one semester. And abstract algebra is very abstract, and there's lots of definitions floating around. It's just a very nice subject to help develop and cultivate your proofwriting skills in this sort of abstract setting. All right. I guess I feel like I should mention one last thing, which is I've been saying abstract algebra, modern algebra. Calling it modern algebra might be a little misleading because the stuff that we'll be talking about, at least in this course, isn't very new anymore. So this course title, calling it modern algebra, actually comes from a book. I think it was written in German actually, with a book of the same title. Written in 1931. 1931. That emphasized the abstract approach. Where everything, you start with axioms and you deduce everything. And this book was written by someone named van der Waerden. It's a very famous book. But, of course, back then, 90 years ago, it was spelled with an E. So maybe the better title for the course would be Modern Algebra as spelled here. Okay. But even though it's old, I mean, the great thing about math, of course, is it doesn't ever change. Once it's there, it's all true, just like the geometry stuff from thousands of years ago. It's still something you learn in high school, and it still has value. But realize that the stuff has been around for quite some time, and it's a huge subject with all these applications, and I'm very excited to be teaching this to you. So we'll continue with the next segment. We'll start in with the basic background leading us to the definition of a group. See you later.